Good morning. I'm Yuvaraj, connecting from Bengaluru, India, on a windy evening. I am glad to be talking at DEFCON A Village. I will be talking on the topic attacks on tiny intelligence. A quick introduction. I'm Yuvaraj Govindarajulu. I'm a senior research engineer and embedded lead at Bosch AI Shield. Alongside me, Manoj Kumar Parmar, the founder, CEO, and CTO of Bosch AI Shield, will join in the second half of this session. I would like to introduce tiny intelligence before we move further on the further topics. When I say tiny intelligence, I mean small embedded devices that are around us that carry small, tiny artificial intelligence or machine learning in them. The tiny embedded devices having small artificial intelligence or machine learning models running on them are popularly called tiny machine learning or tiny ML. We have had small microcontrollers connected to various applications in the past for edge computing, for wireless sensor networks, smart factories, smart agriculture, and so on. These devices have only increased with time, and the possibilities of deploying artificial intelligence on them has steadily increased. The world currently has about 250 microcontrollers and are projected to grow over the next years. In comparison to the other platforms like the cloud or mobile platforms, the number of systems containing microcontrollers are extremely high because of their need and the kind of use cases and applications that they are deployed on. The tiny embedded devices have certain properties. Typical properties of them include tightly constrained microcontrollers. So these tiny embedded devices are tightly constrained in terms of their capabilities, in terms of their peripherals. They have a few hundred kilobytes of memory, very limited storage in few megabytes, and typical processor clock speeds in few megahertz. In comparison to the other platforms like the cloud and mobile platforms, the tiny platform or the tiny devices distinguish themselves largely on various parameters in terms of their characteristics, etc. A typical cloud platform, for example, an NVIDIA V100 has a GPU architecture. The memory is in a few gigabytes and the storage is huge. It's several terabytes, thousands of terabytes, and are typically high power consuming devices, hundreds of watts of power, and are also highly priced. The next platform, the mobile platform, like the smartphones, typically have a CPU architecture, few gigabytes of memory, and few tens of gigabytes or even hundreds of gigabytes of flash. They are usually low power devices because they are battery operated. The tiny devices, for example, the Arduino Nano, has a MCU, a microcontroller core, few hundreds of kilobytes of memory, very few megabytes of flash, and are ultra low power devices. These devices are expected to run for a very long time on limited battery operation. These devices also cost less in terms of few cents or few dollars. Some of the typical devices um, that we look at, and these devices that are AI capable are some of the examples are here. For example, the Arduino Nano, the SparkFun Edge ESP32 microcontrollers, the Sony S-Presence, the STM32 microcontrollers. They typically have an ARM Cortex or a RISC-V based architecture. So the clock speeds between few tens of megahertz to a few hundreds of megahertz. Flash, only a few megabytes of flash and few hundreds of kilobytes of RAM. Very low memory, storage, and clock speeds. We have had such devices around. The STM32 microcontroller, the Arduino that we have had were typically used for edge applications, for control, actuation, sensing of a specific edge application. These devices were typically deployed in open environments. These devices, even in the past, because of the nature of their use cases, they were prone to different kinds of threats. An attacker could typically get full access to the device, especially because that is deployed on an open environment like an open field, open factory, or shops. It's not always possible to detect if the device was stolen. The device in most cases does not have the capability to alarm or to indicate to the main server or a controller that it is stolen. The devices are typically prone to software and hardware attacks. Once the microcontroller is stolen, the attacker can perform software attacks, invasive and non-invasive hardware attacks. People also perform invasive attacks because the whole device is in his premise. This wouldn't be possible, for example, on a cloud device or typically on a mobile device. Of course, the mobile phones are stolen, but the number of devices that we have that are in an open environment in comparison to the cloud that is in a closed, secure enclave are higher. Because the devices have been around and there have been existing threats, classical embedded security has tried to have different security measures in order to protect them. The classical embedded security for microcontrollers had two kinds of protections. Typically, the device protection itself, and also together with the device protection, additional security applications that came with. When we say device protection, the kind of protections that they came with are, for example, memory protection. So the protection for the SRAM or the RAM and the flash itself, protecting the data and the code. Software isolation, the inter-process protection against internal attacks. That was possible. Also, as part of software isolation, we could say a part of the code runs on a uh, secure part and a non-secure. We could isolate the secure core functionality from the unsecure user application and hence also provide a software isolation from that perspective. Interface protection. When a certain interface is not used or when the device is being deployed, these interfaces could either be completely shut off or operate in limited modes. A JTAG port, for example, on a series deployed microcontroller would typically be disabled. System monitoring. Actively, the microcontrollers um, had the capability of tampering detection or abnormal behaviors. It could be in terms of clock jitters or in terms of their memory itself. A system monitoring indicating a tampering or abnormal behavior can then be used to have the microcontroller fall back to the minimal functionality, thereby protecting its internal functionalities. As an example, a readout protection mechanism in STM32 microcontroller. As an application developer or as a deployment engineer, I could then set the protection level for the microcontrollers. When I say there are no protection, the debug port is open, the flash, the registers, and the memory is open for access. When level 1 protection is activated, then most of the memory is is not accessible except for few um, RAM or registers. But when this readout protection is at its highest protection level, the debug port is disabled, all the memory, all the let's say the flash, RAM, registers, etc. are all shut off from external access. Following the device protection itself, like I mentioned, the security applications that came with these microcontrollers, for example, the secure boot, secure firmware update, secure storage, and the crypto services. Crypto services include hardware accelerators to run functionalities like AES, hash, key generation, and so on microcontrollers. As an example, the secure boot of trust of an STM32 microcontroller would, upon reset, run its secure boot, the core functionality that sits in a secure area of the microcontroller. Then through the crypto services, a key is created, which is then used to authenticate that the secure boot and the secure and the user application is authenticated. Once the authentication is successful, then the control is transferred from the secure boot, the secure part, to the unsecure or the unrestricted user application code. We have looked at tiny devices, and we have also looked at the sort of embedded security mechanisms that were there. Now, on a completely different perspective, let's look at attacks on AI systems. AI systems have been very pervasive. We look at the number of applications increasing that use AI. Our everyday life is of lately revolving around a lot of AI applications. These AI systems are prone to different kinds of attacks. The sort of attacks could be given a machine learning model and the training data. The attacks could be on the machine learning model itself or on the training data. One attack on the machine learning model itself is, for example, evasion. A model evasion means that the attacker is embedding spam content, or for example, in an image, he has additional noise, which is then misclassified by the machine learning model due to the perturbation introduced by the attacker. The other attack on the machine learning model itself could be inference, an attempt to determine if an information belongs to a certain record through the machine learning model extraction, probing into the AI system to either reconstruct the model or extract the data that it was trained on. The attacks could also be on the training data itself. The training data could be poisoned. Malicious sample could be injected into the training data, which then affect the performance of the machine learning model, or can be used by attackers to change the performance of the machine learning model, or to to have a secondary attack on the machine learning model through the poisoned intelligence. Talking about model extraction, one of the severe attacks, um, a simple framework about how the attack can be performed. Usually there is a proprietary data set using which there is a trained model, in this case represented by F. And this trained model on deployment is accepting an input and is giving out a response, the input output from a user. But an attacker can query the trained model very similar to how a typical user would query and get a prediction out of the model and be able to get a response out of the model. This query prediction or the request response, the set of queries, can then be helpful for the attacker to create the learned label dataset. This dataset has a new set of XY combination. This new XY combination can be then used by the attacker to train a replicated model, FE, to approximate the original models. And to do this, the attacker need not have any prior knowledge about the data or about the model. This can be a pure black box attack. When the attacker has some knowledge about the trained model or some knowledge on the proprietary dataset that was used, the attacker can then intelligently query using this information to have a more efficient attack. Hence, a gray box sort of an attack. This gray box sort of an attack is then much more severe than that of a black box attack would be. So that, in other words, the attacker would be able to extract more information from the original model than he would otherwise do with a black box attack. A typical example of an attack query for a handwriting digit detection task using the MNIST dataset. An example of an attack query could be as simple as a random noise. As you can see, this is a 28 by 28 patch for a MNIST dataset. When this is fed into a model that was trained on a um, handwritten object or handwritten digit recognition system, the classifier labels this as class 8 or the number 8, the handwritten digit 8. There could be several other techniques to create more efficient attack queries. There could be augmentations of the attack query. There could be even more intelligent queries that force the model to give an output label. Talking about model evasion. In case of an evasion attack, an attacker adds a small noise to a normal original input such that the noise makes the classifier predict or classify an incorrect label than the original label itself. Some of the common evasion attack techniques are fast gradient sign method, PGD, CW attack, the universal perturbation attacks. The fast gradient sign method is one of the very simplest attacks, model evasion attacks possible. The attack needs only the gradient of the model and the original image that has to be perturbed in order to create this attack. An original image X, in this case a panda, was classified with close to 60% confidence. Now, this same image is perturbed with additive noise generated out of these fast gradient sign, which looks like an adversarial patch. Now, this is added on top of the original image to create this second image. The second image is visually, it looks like a panda, but this image has the perturbed noise added on top of the original image. And that is now misclassified as a given with very high confidence. Another example is the handwritten digit recognition itself. For example, the first example here, a 0 with very minimal adversarial noise is now misclassified as 3. So that's the amount of small noise that has to be added in order to create this attack. Having looked at the tiny devices and the embedded security that are there for them, and looking at the AI attacks or the threats for AI system itself, we chose a couple of examples for our experiment to perform attacks on the systems. What we generally see are these tiny devices have certain device protection and security mechanisms coming from the classical embedded security for them. But these security measures do not suffice in order to protect the system against AI attacks. For this experiment, again, we have chosen two different task types. One, a computer vision based task, and another, a time series classification based task. In both of these examples, um, as an attacker, in spite of the existing security measures, can gain access to the communication port in order to send queries to the system and look at the response in order to build the learned labeled data set to create uh, an extracted model or steal the model. This is the setup for the image classification task. We have an ESP-I microcontroller which is acting as a camera, which has a camera, CMOS camera on it, that is streaming video in MPEG format. The video is transferred or sent over a fixed IP to the Raspberry Pi. The digit recognition, the model, is deployed on the Raspberry Pi itself. The channel, so in order to gain access to this device, we know what is the IP address through scanning the identified what is the IP address used. Now, as an attacker, I would get access to this Wi-Fi channel to then query the system as though I was a camera and look at what is the response that is coming. Like very similar to the framework of model extraction that we looked at. As a second setup for time series classification, we had the gesture recognition with IMU sensor, the initial measurement unit. The boards that we used are ESP32 dev kit connected with a MPU 6050 6-axis measurement unit connected via an I2C interface. The model is deployed on the ESP32 where the inference is running. The IMU sensor can be then replaced with another microcontroller and fool it as though I am an attacker, or fool as though the values are coming from the IMU sensor itself. So that's the channel. The I2C, the I2C is the channel through which the attacker gets access to the device to send queries and get responses. The model deployed on the ESP32 microcontroller is about 10 kilobytes. That's running the gesture recognition system. For both of these tasks, the computer vision and the time series classification task on the two setups that I showed you, we performed the extraction and evasion attacks. Quick numbers on the extraction and evasion attacks. Firstly, the size of the model that was deployed on the Raspberry Pi was about 1.8 megabytes, and that deployed on the ESP32 was around 10 kilobytes, very small model. The original model had accuracies of 99.21 and 99.15 respectively post deployment. Through gaining access to the ports, namely the Wi-Fi port and the ESP, in case of ESP, the I2C communication port itself. Through the request response framework, we were able to extract the model and recreate a stolen model which had the which had an accuracy of 88.92%. We had the same of about 65% for gesture recognition. 88 and 64, that means the attacker was able to recreate a model just by passing these input and output queries. The attacker can then further use his own dataset and use as a transfer learning to further increase the model accuracy. We also performed a simple evasion attack using the FGSM technique, and the evasion accuracy or the number of instances misclassified was on the digit recognition system 75.85, 78.5%, and that on the gesture recognition was about 85%. Each of them had different strengths, different magnitude of the attack represented by the epsilon. That again is the characteristic of the data set and the kind of model that is deployed itself. These are some of the snippets from the attacks that I previously showed you. The original model 2 through an FGSM attack with adversarial perturbations looked like this here, and this was misclassified by the model as class 1, as though this was digit 1. Similarly, with that of the gesture recognition, we can look at the 6-axis and before, that is, this is the original input, and we can also look at the 6-axis after adversarial input. After adversarial input, the class was misclassified from 2 to class 8 in a time series classification case. Some of the additional remarks, some of the additional findings that we have from these attacks are the model extraction on these small models on tiny devices could be extracted with lesser number of queries than that of large models that would typically be deployed on clouds, on a cloud system. Generally, because of the size of the model itself, the complexity of the model, number of classes that they are dealing with, attribute to the lesser number of queries that are needed to recreate the model. Model evasion. Once the communication ports are accessible, the evasion attack examples can be easily crafted. And when somebody attacks using the evasion attack, for example, the FGSM strategy, those go undetected by the system, typically because they do not have complex statistical methods to detect these evasion examples or these adversarial inputs. The attack efficiency can also be further increased by having more stronger attacks, the epsilon, for example, and with more with other kinds of attacks. For example, the universal adversarial perturbation is a much more complex or a powerful attack when in comparison to the fast gradient sign. Not only that, for data poisoning, we looked at even in the cases where tiny devices are deployed, and when these devices are in the open field and are constantly um, sensing and generating data, because they are in an open environment, this data could be poisoned. And the data set from these small devices and these poisoned inputs could go undetected. In conclusion, tiny intelligence on tiny microcontrollers are prone to attacks. In most cases, the traditional embedded security cannot detect attacks on their AI. With minimum or no effort, the ports can be hacked to gain access to these devices, which makes the attacks much more easier. Thank you. That was my talk on attacks on tiny intelligence. Thank you.